Hello everyone, today I am going to present my project on machine learning based CPU scheduling. CPU scheduling is an important concept in operating systems. It decides which process gets CPU time, and the goal is to minimize waiting time and improve efficiency. In this project, I compare a traditional scheduling algorithm, which is shortest job first, with a machine learning based scheduler. The main objective of my project is to implement the SGF scheduling algorithm, to build a machine learning model that predicts CPU burst time, and to compare the performance of both approaches using average waiting time. The idea is to see whether machine learning can improve scheduling decisions. Let me quickly explain the project structure. app.py, this is the main file that runs the project. sgf.py contains the SGF scheduling logic. mlscheduler.py contains the ML-based scheduler. Burstpredictor.pkl, this is the trained ML model. Trainedmodel.py, used to train the model. So basically app.py calls both schedulers and compares the results. Shortest job first scheduling works by selecting the process with the smallest CPU burst time. For example, if we have process with burst times 6, 7 and 4, SGF will execute the process with burst time 4 first. This reduces the overall waiting time and is considered optimal for many cases. However, it requires knowing the burst time in advance, which is not always possible. To overcome that limitation, I implemented a machine learning based scheduler. Here I use a model from scikit-learn, specifically a random forest regressor. The model is trained using historical processes like data such as previous burst time, priority, arrival time. Based on this data, the model predicts the next CPU burst time. Then, instead of actual burst time, the scheduler uses the predicted values to decide the execution order. Now I will run the project. I execute the main file using python app.py. This runs both schedulers and calculates the average waiting time. Now I will show the output in the terminal of VS Code. The output shows SGF average waiting time 4.33, ML scheduler average waiting time 4.69. This means that in this case SGF performed slightly better than the ML based scheduler. This is because machine learning depends on the quality of training data. If the model is not perfectly trained, its predictions may be not optimal. In conclusion, traditional algorithms like SGF are very efficient when exact data is known. Machine learning can be useful when burst time is unknown. However, ML performance depends on training data and model accuracy. The project shows that ML has potential in CPU scheduling, but it still needs improvement to outperform classical algorithms. In terms of future improvements, there are several ways in this project can be enhanced. First, the accuracy of the machine learning model can be improved by training it on a larger and more realistic dataset. Currently, the model may be using limited or synthetic data, so adding real-world CPU scheduling data would make predictions more reliable. Second, instead of using a single model like a random forest regressor, we can experiment with other machine learning algorithms such as decision trees, neural networks, or even deep learning models so that if they perform better. Third, we can make the scheduler dynamic, meaning it can learn and update itself in real time as a new process data comes in, rather than relying on a pre-trained model. Another improvement would be to add a graphical visualization such as Gantt charts to clearly show how processes are scheduled over time. This would make the project more interactive and easier to understand. Finally, we can extend the system to support more advanced scheduling techniques like priority scheduling, round robin, or hybrid approaches that combine traditional algorithms with machine learning. Overall, these improvements can make the system more accurate, scalable, and closer to real-world CPU scheduling systems. Thank you for watching my presentation.